Testing. Testing. Good morning. All right. How's everybody doing today? Hope you guys are doing okay. Do I say the same things every single gosh darned lecture? I probably open the same way every single lecture. But to be fair, next week is Pandemiversary, so yeah. I thought I had escaped recursion for the time being. Then we started talking about it in my math reasoning course, and now I'm sour about it. Well, at least you heard it from me. You heard it here first. Yeah. I mean, it's a really useful way of constructing things mathematically. So, it's good to know. It's a tool. Think of it as a tool in your tool belt. Yeah. Okay. Is my sink... How's my sink today? I would just want to check the sink. I see it's kind of blurry. Usually that means the sink might be off. No, it's pretty good, actually. Okay. Alright, well... what did I do? Did I do something? Oh, I just paused that. Okay. Alright. I should wear a hazmat suit to celebrate the pandemic. They should make the start of the lockdowns a holiday after the pandemic. Yes, a holiday with no traditions. It's like you just sit in your house and do nothing all day, and that's how you commemorate the pandemic. It's been a year of COVID, but it's COVID-19 for a reason. Can't it leave already? Well, you know, I don't know. I don't really get a say, you know? Like most of us, I've just been, I was just trying to do my best to ride the tiger, you know? Try to keep my head above water and keep my family together to the extent that I've been successful at that. Let me tell you, it has not been easy. Things have not gone perfectly during this time. And I share I share in the sentiment that I would like this whole situation to just be over already. But, you know, it's not really up to me, is it? You just kind of have to take it. You just kind of have to, you know. My cat just meowed at me. He's like, "You're being too depressed on stream." Yeah, I don't know. Just keep going. Keep trucking. If you're living in an area that's still, you know, bad, just don't lose hope. Don't lose faith in humanity. Because that's an easy thing to do these days. Anyway, so couple of questions about the test. What if you were to MSAF a test, what would happen? Well, first of all, in order to MSAF a test, you would have to have not submitted the test. The submission of the test in any way, shape, or form that voids your right to MSAF it. So don't do that. But the marks that test, or the percentage of your final grade that test is worth, gets distributed evenly across the other two tests. when are you going to get the T2 marks? Within probably a couple of days, probably by tomorrow, sometime tomorrow. Basil has sent me the preliminary report, and it turns out, apparently, that once you correct for zeros, that is, people who did not attempt the test, the average on the test is 82%, which is actually, considering the amount of belly aching that was going on about the test yesterday in class, that's actually surprising. I would have expected, more of a, mid-70s, like, average. Normally, the belly aching really starts ramping up if the average dips below 70. But, yeah, my cat doesn't like the pandemic either. I don't know. I'm not sure how the cat feels about the pandemic. We have been around the house for a year, which is like, in Martin's case, that's about half of his life. So, yeah. Can you still fetch the test even if you MSAF it? So the idea is that you're either not able to write the test or you're able to write the test, right? If you're able to write the test, you are obligated to write the test. If you are not able to write the test, then you MSAF it. And if you are not able to write the test, then you should not have fetched it either. You shouldn't, fetching, some profs are going to consider fetching to be indication that you attempted. Some profs will not. So I would not recommend even looking at it if you're intending to MSAF it. Incidentally, I will just say the thing about MSAFs that I always say. It is an exception that is designed for medical accommodation or, mental health accommodation. The purpose of the MSAF is not to give you a get-out-of-jail-free card that you can just use at some point in the semester as a grade boost. That is misuse of the MSAF policy, just so you know. So there you go. That is the opinion of your professor. Are we almost there, though? That's the question. It feels like this thing's just going to go on forever now. So if you MSAF test 3, your other 2 tests gain weight. Yes, that's true. If you MSAF test 3, could you also MSAF the assignment due that week? If you take a look at the MSAF policy, MSAFs are effective for a 3-day period. Any assessments in any class that occur during that 3-day period are applicable to the MSAF. Does one of your tests get dropped? No. One of your tests does not get dropped. Nope. One of the assignments gets dropped, but none of the tests get dropped. If that were the case, I wouldn't put so much effort into creating them. So, right. We should get into our lecture material then. So we just cleared up all of this business about floating point, so let's talk about some approximation algorithms. Remember this? Remember this from the first slide of this course? Formulating a problem. What is the x-intersect of a function f? Assuming that function is monotonically increasing on some interval from a to b, and that f of a is less than 0, and f of b is greater than 0. To determine the x-intersect with precision e, e being greater than 0, so long as b minus a is greater than e, do steps 2 to 4. So we calculate the midpoint. If the midpoint is above the if it's above the x-axis, which you can tell by it being a positive value, we move the interval we move the b in towards a, because we know that, as it is depicted in this diagram, that the intersect must be somewhere between a and m. Conversely, if the point at m is negative if it's below the x-axis, we know for a fact that the x-axis crossing must be on the interval from m to b, so we move a up to m. So let's revisit a question. Can you take the exact x-intercept by setting the epsilon equal to 0? In light of our newfound knowledge of floating point arithmetic, this should be obviously not the case. You should be able to say, well, obviously you can't take the precise anything, exact precision on anything on a computer, because the number system you're using to represent numbers in the computer system itself is of finite precision. It does not have exact precision. So, obviously, you can't do this. It's like you are asking the computer to do something of which the number system itself is not capable. What would actually happen if you ran this algorithm setting epsilon to 0 is that you would be jumping back and forth across the floating point error. Like, you would never be able to diminish the gap beyond the quantum of floating point representation, which, is very, very small, but not exact. And as a consequence of that, the thing would just run forever, because the exit condition for the algorithm would never be met. When is the exam? Is the exam April 28th? GU. All right. I didn't get an email about that. I should check my schedule. Normally I get an email telling me when that my exam has been scheduled, and I go look it up. But I guess, whatever. So, the approximate x-intercept. In Python, functions can be passed as arguments. So, we can create a generic x-intercept function to which we can pass any function f. So the idea is that we can pass a function into this function and, take this algorithm that we have been discussing since the beginning of the course and actually have a Python implementation now. So, just because we have to keep moving, I'm gonna not do this one in code. We'll just review it. So we have x-intercept, the function, takes f, the interval around which we know the x-intercept is, and whatever the epsilon we wish. While b minus a is greater than epsilon, while the interval is larger than the error, we find the midpoint. If f at the midpoint is less than or equal to 0, we move a up to m. Otherwise, we move b down to m. When this is finished, when this while loop is finished, that is to say, when b minus a is finally less than or equal to the epsilon, we return the bounds. And, if you, rather than returning the bounds, if you wanted to approximate the x-intercept as the midpoint of the new interval, that's perfectly reasonable as well. Certainly, the probability is higher that it will be closer to the midpoint of the interval AB than than it is closer to A or it's closer to B, but, that's kind of neither here nor there. So, if you wish to use this function, we can define the functions which we find the x-intercept for in a form that's rather familiar for anybody who's taken a math class. So this would be a simple polynomial function, x squared minus 4, and this would be x squared minus 2. These are functions. We can pass these as arguments into the x-intercept function. We know that we have a pretty good idea that an x-intercept will be somewhere between 0 and 10. Keep in mind that this algorithm only works if the interval over which you're testing is monotonically increasing. So, okay, they're gonna make me do it anyway. All right. Okay, fine. Documents, master, 1MD3, winter. Oh, that's wrong. Semester. 1MD3. Code. Get it. Topic 6. I was hoping I could get away with not having to do this, but you know, whatever. Boom! Fixing the indentation. There we go. So, we've got F1, we've got F2. So, if you just think about, like if you were to graph these functions, you'd see easily that, you know, the x-intercept of the first one should be 2, and the x-intercept of the second one should be root 2. But let's actually do this, eh? And just to show you what's going on, let's add some print statements. So print A is equal to A, B is equal to B, F at M is equal to F at M. There we go. Let's just print one of these for now. And I think that, yep, let's save that up, try her out. Python 3 topic 6.py. So, okay. Gotta put these in here. In order to actually see what's going on. So, we start off with A is 100, A is 0, B is 100, B goes to 50, B goes to 25, 12.5, etc. on down the line. Down, 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 down. You can see F is getting closer and closer to 0, and that our bounds are closing in on 2. So, this is good. Yep. Eventually, we hit the point where this is less than, the difference here is less than the epsilon that we're looking for. And there you go. We can therefore say that the x-intercept is somewhere in the vicinity of 2. If we run this on the other function, you can see that we get somewhere in the vicinity of root 2. So, there you go. We actually did the function example from the first slide finally, eh? Let me see if there are any questions. Would you just be inputting a reasonable estimate for A and B? Also, what happens when there are 2 x-intercepts? Good questions, Jacob. So, number 1, sort of. To some extent, you don't know what the function looks like it's doing because, otherwise, if you knew what the function looked like, you wouldn't need to take the x-intercept, right? But it is a requirement of the algorithm that whatever interval you pick, the function must be monotonically increasing on that interval. So, like, for example, if we had a parabola and we chose an interval from here to here on the parabola, that wouldn't be monotonically increasing, right? Because it's in, like, both sides work. So, the fact that it's monotonically increasing on the interval ensures that there's only one x-intersect. If there are two x-intersects on the interval, then the function is not monotonically increasing, which means that we have improperly applied the algorithm, because the algorithm is only applicable in cases where the function is monotonically increasing over the interval. Does the function just shift a and or b towards the midpoint? Yes, basically. It just moves the bounds in a precise manner until it comes to an approximation of the x-intersect. Cool. So, let's talk about another approximation algorithm. Square root. So, some of you may be aware of this, but square roots are actually a reasonably difficult thing to calculate. Like, if you were to take out a piece of paper and you wanted to just calculate the square root of 37 without using a calculator, that's a reasonably difficult thing to do. That's why, that being said, square roots are an extremely useful mathematical entity. This is why in elementary school they kind of teach square roots monolithically as an operation that you don't know how to perform, because, I believe the solution to calculating a square root requires, like, binomial theorem and binomial expansion and algebra stuff that you don't get until later on in high school, or, I think early high school, maybe. Anyway, so it's useful then to have an approximation algorithm for square root, because, again, sometimes by approximating things you can come up to the same answer with less work. Your calculator only holds so many digits of precision anyway. One way to compute square root is to observe the property that the integer a is an approximate square root of n if a squared is less than or equal to n, and that is n is less than a plus 1 squared. So basically, this is like a combination of square root plus floor, right? So it's like it's like Price is Right rules. We want the closest a such that a squared is less than or equal to n, and a plus 1 squared is greater than n. So it's like whichever a is, closest to without going over the actual, like, decimal real number square root. So, we can perform this with a while loop. Notice for these examples that we're using while loops and not for loops, because these are kind of numerical examples. We're waiting for specific mathematical conditions to become true, so these aren't tied to data structures, right? These are tied to mathematical properties, which is why we're using while loops. So, wouldn't it just need to be monotonic? It doesn't matter if it's increasing or decreasing. Well, the idea that it's monotonically increasing, that assumption is baked into the conditions, actually. So if you take a look at the conditions here, right, you could, in theory, you could add in some extra if conditions that say, if a is less than b, then it's monotonically increasing. If a is greater than b, then it's monotonically decreasing. And then you reverse the inequality condition according to which situation you're in. You can certainly write an algorithm like that, but that's not this algorithm. This one does assume monotonically increasing, and that is encoded in the nature of the if condition here. Scoop! Ha! I caught you. You came too close, and now you will be on stream. Hop, up. There we go. Hello. Say hello to all of the people. Say hello to all of the people, Mars. Yep. Anyway, so for linear square root, basically all we're doing is looping over values of a until we hit one that satisfies the property that we're looking for. You know? Fairly simple. It's actually not complicated at all. However, one might say it's not terribly efficient because, you know, if you're dealing with a large number, you can, like, if you are dealing with, like, 38,276 as a number, it is not perhaps useful to start a at 0 because, you know, it's not the square root of 1. 1 is not its square root. 2 is not its square root. 3 is not its square root. In fact, you could probably start this guy at 2. But anyway, so let's see how much more efficient we can make this thing, right? But just to see how it works, let's imagine we're taking the square root of 27, right? So a starts at 0, goes to 1, goes to 2, goes to 3, goes to 4. By the time we hit 5, a plus 1 is 6. 6 squared is 36. 36 is greater than 27, but 5 squared is 25, and therefore, you know, we don't hit it on the previous iteration. So, I'm going to skip the quiz. B is executed exactly as many times as whatever the output of the function is. Hence, A is executed, the statement A above, or perhaps A is written to, the square root of n times. Square root here meaning integer square root as opposed to real square root. So, this is fine, but we can also perform a binary search over these values. So remember binary search from the last set of lectures, right? Because, you know, essentially we're operating over the what do they call those? The natural numbers, right? The natural numbers exhibit many of the properties of a list which is in order. The natural numbers are, for example, in order. So, when searching through things that are in order, we can, in fact, perform a binary search style method on it. So, if we suppose that we have an A and B such that the root is between them, and it's actually it's reasonably simple to come up with a B that, you know, the square root has to be less than, because a B such that the square root is of, like, to select a B such that the square root of n is less than B, all you have to do is set B to n, right? Because unless you're talking about like 1, a number's square root is always going to be less than the number itself, or values less than 1, I suppose. You know, not so for integers that works most of the time. So what you can do is then take the midpoint, right? You can deal with it as an interval, right? An interval from 0 to 8 in this example. So imagine we're performing the same operation. We're trying to find the integer square root for n is equal to 27. So the midpoint here then will be 4, right? The midpoint between 0 and 8 is 4. 4 squared is, of course, 16. So we have to keep trying. We then move 4 into the position of A. We then have a new midpoint at 6. 6 is 6 is greater than, so we then execute statement E, which is we set the upper bound to C. And you can see that we're kind of, in the same way, sort of narrowing in on the particular value that we wish. Exiting, of course, when a plus 1 is equal to b, because when a plus 1 is equal to b, we know we have an interval of 1, and that's the, natural stopping point for this type of algorithm. So, this is good. So what we've effectively done is we've gone from an algorithm that must be executed root n times in order to find the root of n, to an algorithm that must be performed log base 2 of q, where q is the size of the interval, right? So if you make b into n in the same way that I was describing earlier, and if you allow a to remain at 0, then what that gives you is an effective runtime of log base 2 of n in order to run this thing. And that increases more slowly than a square root. So this is a better algorithm. Here's a implementation of such. We'll just keep moving. Yes. So this is another modification of the algorithm, which even improves on the selection of the bounds. So rather than just setting b to n, what we can do is we can actually do a quick loop that sets b to some value which is greater than n, greater than the square root of n, but is still, it's not necessarily reaching n, right? So you could, it's kind of a toss-up, actually. It depends on where n falls, but this can save you a few execution cycles as well. So, essentially, this, on average, this algorithm, by selecting the bound with reference to n, this makes our approximate number of executions into log base 2 of the root of n, which is pretty good. It's proportional to log base 2 of the root of n. Remember, when we talk about these types of things, we're talking in generalities about algorithms. It's not exactly log base 2 of the root of n. It's proportional to log base 2 of the root of n. Let me see if I have any questions. Going back to the previous example. So depending on the function, you would have to alter your statement. Well, yeah. You would have to have certain foreknowledge about the function in order to correctly apply the algorithm. That's how I would put it. So let's talk about Pythagorean triples. So everybody should know Pythagorean triangles. Pythagoras, a triangle with a square angle. The hypotenuse is proportional. The square of the hypotenuse is proportional to the sum of the squares of the remaining sides. Pythagorean theorem. Famous Greek people, etc., etc. So we can write an algorithm that sort of prints for us all of the triangles that satisfy Pythagorean theorem by essentially looping over all the possible A's, B's, and C's, and selecting those which satisfy Pythagorean theorem. So let me just put that in there. So this is interesting because this is like the first example that we've had in the slides of a triple loop. So we've got a loop within a loop within a loop. You guys hopefully will have been paying attention in one of the tutorials where they do double loops. But the idea is for each value of A, this loop gets fully executed. For each value of B, this loop gets fully executed. So the number of iterations here is actually n cubed, right? This if statement gets executed n cubed times. So yeah. So if we want to print, or actually it already prints, we don't need to do that. Print Pythagorean triples 1. We'll just call it triples because I'll make the modifications to it as we go. We will call that on, say, 100. There we go. Execute. Name error. Whoops. Yes, I need to adjust accordingly. So here you go. Here are all of your Pythagorean triples for side lengths going up to 100. Very neat. Very cool. But did you see how long that took? That was way too long. So let's see if we can improve things. Again, I'm skipping through the quizzes because they take too much time. If we were in class, we would do them. Like if we were in a physical classroom, I would do them because they would take not much time. But since we're online and we need to keep moving. So here's an interesting observation. Do we really need to loop over every value for C? Do we really need to? Or can C be calculated from A and B? It would seem to me that the value for C can be calculated from A and B because we have that nifty formula. So we don't actually need to loop over all possible values of C in order to determine whether C works for a particular triangle. We can actually just calculate it. Boop. So this becomes a bit of a problem, though, right? The problem that we now run into is that this if statement will always become true, right? If we execute this, it's like, we're now into the realm of floating point numbers. That's what this does, is it makes it a floating point number, right? So now that we're in the realm of floating point numbers, actually none of the equality comparisons are coming out, so there you go. So we have to modify this condition. So basically, we're looking for the Pythagorean. These Pythagorean triples, they need to be integer values, right? So basically what we need to do is we need to perform a test to see if C comes out as an integer, right? So if C modulo 1, C, like if you perform modulus on a value like this, like mod 1, that will give you whatever the decimal is, right? Quick way to do it. So if C mod 1 is greater than, well, if the absolute value of C mod 1, we shouldn't have any negative values in this one, but, just to be careful. Say it's greater than, some small thing, because, again, these are floating point numbers now, so you have to be careful about floating point bounds. We shall do that. All right. It's not working for thumb reading. Maybe it's because I'm doing it a different way from the slides, eh? Maybe I should just follow the slides. Oh, they're using the binary square root method to see if it's equal to itself. I prefer my method. Let's just see what C is. Large. Oh, your professor's a big dummy. Your professor is a big dummy. He forgot to do the bit where you take the square root. Alright. Cool. Alright. That was it. That was the problem. So, you can see that this has had an interesting effect on the actual numbers. So, these are no... Alright. Alright, I was trying to be fancy, but, you know, so it goes. I'll just do what the slides say. I'm not going to use binary square root, though. Although I guess I have to. I'll just use floor of c to the power of 0.5. If c is less than or equal to n. That's important, right? That's why I'm getting all of these values that are large, is because I'm not performing that bit. And c2 is equal to c times c. That is to say, c2 is the perfect square root. It's the floor of the square root of this function. We shall see what goes on here. Floor is not defined. Oh my god. Port math. Still no? Bloody hell. Is it math.floor? Local variable c referenced before assignment. Oh, yeah, that makes sense. There we go. There we go. All right, there we go. Here are our Pythagorean triples once again. So, there we go. Now, you may notice one more thing about this. Although we've now reduced this from an n cubed algorithm to an n squared algorithm, we might be able to do even better than that. If you take a look at the list of Pythagorean triples that are being displayed here, there are certain duplications. So you'll notice we've got 3, 4, 5 and 4, 3, 5. Now, in some circumstances, that may be permissible and acceptable, but it might also be considered a repetition. You might not, like if you want to exclude mirror images, if you consider a triangle which is a mirror image of another triangle to be the same triangle, then you may wish to exclude them. And the way that you can exclude them is actually very simple. All you have to do is change one character. Rather than looping from rather than looping through every single possible value of b to find the ones that work, we can start at a for whatever a is. And you can see this eliminates all of the duplicates. And so you end up with a more concise list. So yeah, and that further reduces the search space that you have to go through to find all of the Pythagorean triples, thus increasing or decreasing the amount of time that you need to run the algorithm. So there you go. Let me see if we have any questions. Wah, wah, wah. Yeah, go. So, if we know how many steps a program takes, depending on the input, we can use this to predict the execution time. This can be done without knowing the details of the processor and the compilation to machine language. So, this is this big O stuff that I've been talking about all this time, right? If you actually graph n cubed versus n squared versus n versus log base 2 of n, if you take n to be, for example, the number of the maximum size of the Pythagorean triangles that you're looking for, or the size of the list that you're searching, or something like that, you can see that some of these cases are much more desirable than others, right? So again, we are dealing with a proportionality to these functions. It's not exactly these functions. Each one of these have kind of baked into them the idea of a constant term that you multiply. It's not n cubed. In the case of the Pythagorean algorithm, it's not n cubed, just straight n cubed. It's n cubed multiplied by however long it takes to execute each loop iteration, right? And however long it takes to execute each loop iteration is going to be system dependent. It's going to be dependent on the manner in which the algorithm is performed. It's going to be dependent on the programming language that it's been written in. It's going to be dependent on, the specific details of the operating system on which the program is being run. It depends on a lot of things. And basically, the way that we analyze algorithms is we take all of that complexity, we smush it down to a single constant term, which means, it's like, it's a term that says, and all of this stuff that we can't control for, we're going to call it C, and we're going to deal only with, like, the proportionality of, the structure. So, and the reason to do that is basically the bigger n gets, the more any constant terms are not going to have an effect on the runtime. So, if it takes 30 milliseconds for the algorithm to start up, initialize its variables or whatever, if the thing is running for 3 hours, nobody's going to notice the 30 milliseconds, right? So that's the kind of logic that's going on here. So, yes, questions? If you wanted to keep the duplicates, couldn't you just add a second input statement with print BAC so that's fast but still keeps the mirrors? Yeah, you absolutely could, actually. That's using the observation that in mirrored triangles, A and B become B and A, and that, yeah. So you don't actually have to calculate them, you can just use them. Absolutely, 100%. I'm teaching! Yeah. So, yeah. Good. So, there's a set of slides here that I'm gonna just gloss over because, essentially it's like quizzing you on whether you know what the difference between a cube and a square is. Like, if we run this guy for n is equal to 200, what's the proportionality, how many times is a particular statement going to be executed, stuff like that. I'm just going to skip it because, I would like to get this finished today. So, be careful with floating point. Just a few final notes on how floating point is dangerous. All right? So, take our old friend, the quadratic formula. It is possible to mess with it in a computer system. So, if we sort of take a nominal case of a quadratic equation, it'll work. But once we start dealing with large values and, like, differences between large and small values, if you remember, remember how we can gobble small values inside of large ones? Even though this 2 to the negative 2 times 10 to the power of 8, that's not necessarily, that's not big enough by itself to gobble up, something times 10 to the power of 0. when you multiply it by itself, it becomes that large, right? So 2 to the power of, or 4 to the power of 16, which is b squared, is enough to gobble up the negative 4ac term, which means that the solution that you're going to get is not going to be accurate. You're not going to get the correct solution. And it's because you have multiplication in the middle that has large intermediate values that other values can get swallowed up in. And I know I'm going slightly over time. Give me just 2 seconds to explain this. So how can you avoid this? You can use the decimal library for exact precision, which is slower, or you can use alternative formulae that are more numerically stable and don't have these large intermediate values. So it turns out that you can find the solutions for the quadratic equation using Vieta's formula, which is an alternative. There are alternative ways of calculating a lot of these things. So it turns out that you can avoid the big multiplication in the middle by using Vieta's formula, and, you know, that works. But the whole problem is that because b gets multiplied against itself, if b is much larger in comparison to the other numbers, the b squared term can gobble up any of the other terms. So that can lead to floating point inaccuracies, and floating point inaccuracies are notoriously difficult to spot. So there you go. All right. I'll take some questions, and then we can say that we have done and dusted with topic 6. You found topic 6 quite confusing. Well, you know, there's a lot of stuff in there, you know. Some of it, especially like the binary representations stuff, that kind of thing, you know, in order to give it a proper treatment, this would have to be an electronics class, you know. So, yeah, it's, you know, yep. In practical terms, you know, there are a few big takeaways, like, don't imagine that performing exact equality over floating point numbers is useful, you know. Hexadecimal is your friend, not your enemy. Stuff like that. And, you know, yeah, like this is the kind of stuff that, yeah, it's, you know, we're starting to get into some of the more advanced topics in this course. I think topic 7 isn't too bad. Topic 7 is the, testing and exceptions. Yeah, testing and exceptions, then classes. So, testing and exceptions isn't too bad. But yeah, this is like very mathy stuff, you know? Would you be told not to use the decimal library or in tests or assignments? I would not tell you not to use the decimal library because I wouldn't discourage you from using the decimal library. Learning how to use the decimal library can be extremely valuable. So, no, I'm not gonna... Nope. Like, I've asked on, like, tests and exams in the past questions related... Like, questions that have a catch in them. And the catch is, unless you are careful with floating point numbers, you won't get the correct answers. Right? So, So if a question involves floating point numbers and it seems too easy, what's being tested is probably your knowledge of floating point. But generally speaking, it sort of once again comes down to, I have presented you with a few different ways of dealing with floating point representations. It's up to you to select the one that you believe, works best in the particular situation that you're in. So, normally with floating point style questions, people come up with like a whole bunch of different ways to try to get around the problem. But I don't always say that the question is about like. Well, no, I shouldn't say that. Usually there's some kind of hint in the question that I'm testing you on floating point. So yeah. Yep. Any other questions? Yeah, Aaron, the most probable cause of you finding topic 6 confusing is because it is. Your assessment is correct, I would say. Okay, well, I think I'm going to call it here. Thank you, everybody, for paying attention to me today. Tomorrow, we don't have lecture. But the day after, oh boy, Thursday, we're going to start topic 7. Take her easy, folks.